Sumerian tablets are probably one of the oldest form of written record that we have. They've been translated, and they tell exciting stories about how gods intermingled with human beings and actually had a hand in the creation of human beings.
In 2017, a mathematician at the University of New South Wales in Sydney was preparing a lecture for first-year students when he came across a photograph of a small clay tablet. It had been sitting in a university collection in New York for nearly a century. At first glance, it looked insignificant, just another ancient artifact, covered in strange symbols. But what researchers eventually discovered on this tablet would challenge everything we thought we knew about the origins of mathematics. The tablet was covered in rows of cuneiform numbers, pressed into clay by a Sumerian scribe, roughly 3,800 years ago, in the ancient city of Larsa. For decades, scholars had argued over what the numbers meant. Some said it was a teacher's cheat sheet. Others dismissed it as an accounting record. This mathematician, Daniel Mansfield, thought they were all wrong. He believed the tablet was something far more significant. And after months of analysis, alongside his colleague Norman Wildberger, he published a paper that sent shockwaves through the academic world. The tablet, known as Plimpton 322, was not a list of random numbers. It was a fully functioning trigonometric table, a precision engineering tool created over 1,000 years before the Greek mathematician Pythagoras was even born. That discovery forced a question that mainstream archaeology still has not fully answered. How did a Bronze Age civilization, one that had no iron tools, no telescopes, and almost no access to stone or timber, produce engineering documents that modern scientists can verify as technically sound? And if this single clay tablet is telling the truth, the history books may be missing a much bigger story. Before we continue, if you're enjoying this journey into ancient mysteries, please subscribe to the channel. We're getting closer to 1,000 subscribers, and your support means a lot. The answer is buried across dozens of museums, thousands of untranslated tablets, and at least one headless statue in the Louvre. The statue sits in the Mesopotamian wing of the Louvre Museum in Paris, carved from dark green diorite, a stone so hard that Sumerian sculptors would have needed weeks to shape it. The figure is seated, hands clasped, dressed in a simple draped garment. The head is missing. It has been missing since the statue was unearthed at the site of ancient Girsu, in what is now southern Iraq. What makes this statue extraordinary is not the figure itself. It is the object resting on the figure's lap. Carved into a flat clay tablet that the statue holds is a detailed architectural floor plan. It shows the walls of a temple complex, complete with fortifications, towers, entrance points, and small structures nestled between buttresses. Alongside the tablet sits a graduated ruler and a stylus, the tools of an ancient architect. The statue represents Gudea, the ruler of the city-state of Lagash, who governed between approximately 2144 and 2124 BCE. And the plan on his lap is not decorative. It is the oldest known architectural blueprint in human history. Gudea was obsessed with building. The inscriptions found alongside his statues describe a ruler who poured the resources of an entire city-state into temple construction. His greatest project was the Aninu, a massive temple dedicated to Ningirsu, the patron deity of Lagash. The details of this project were recorded on 2 large clay cylinders, now known as the Gudea cylinders, which contain some of the longest-known Sumerian literary texts. What those cylinders describe is not the vague spiritual ramblings you might expect from a Bronze Age king. They contain specific construction instructions, materials lists, descriptions of foundation techniques, and references to drainage systems and load-bearing principles. And when archaeologists excavated the actual site of the Aninu at Girsu, they found something unexpected. The ruins matched the blueprint, not roughly, not symbolically. The proportions on the clay tablet aligned with the physical footprint of the excavated temple with a precision that caught researchers off guard. More troubling, the engineering at the site showed techniques that had no business being there. The foundations incorporated drainage systems that would not become standard practice for centuries. The structural design showed evidence of earthquake-resistant features, significant for a region that sits near active fault lines. The load distribution in the walls suggested someone understood principles of structural engineering that historians traditionally attribute to much later civilizations. That is one tablet, one statue, one temple. The Sumerians left behind 500,000 more tablets, and the deeper researchers dig into those collections, the stranger the picture becomes. Take the Nippur map. In 1899, archaeologists from the University of Pennsylvania began the first full excavation of Nippur, one of the most important religious centers in ancient Mesopotamia. During that dig, they pulled a small clay tablet from the earth, roughly the size of an adult hand. The surface was covered in etched lines and cuneiform script. For over a century, scholars debated what the tablet showed. The lines seemed to depict the walls and structures of a city. But when researchers tried to match the tablet to the excavated ruins of Nippur, the proportions did not seem to line up. Many experts concluded the map was simply inaccurate. Then, in the 1970s, a University of Chicago archaeologist named McGuire Gibson was reviewing aerial photographs of the Nippur site, and he noticed something. The map was not wrong. The excavations had simply not yet uncovered the portions of the city that the tablet depicted. When Gibson matched the tablet to the aerial view, the city walls jutting southward on the map lined up with surface features that had never been dug. Subsequent analysis confirmed it. The Nippur tablet, dated between 1500 and 1300 BCE, is a scale-accurate representation of the ancient city. It shows distances between gates in the city wall, the layout of canal networks and irrigation channels, and the positions of major temple complexes. According to Augusta McMahon, a professor of Mesopotamian archaeology at the University of Chicago and the current director of Nippur excavations, the map's creators likely used knotted ropes, measuring rods, and possibly early forms of trigonometry to achieve this accuracy. Consider what that means. Over 3,000 years before satellite imaging, before GPS, before any modern surveying equipment existed, someone stood in the streets of Nippur with a length of rope and a reed stylus, measured an entire city, calculated the proportions, and transferred them onto a portable clay tablet at a precise scale. And they did it so accurately that a modern archaeologist with aerial photographs needed decades to catch up. The Nippur map may have been more than a record. The historical context suggests it was a planning document. Before the tablet was made, Nippur had fallen into near-total abandonment. When the Kassite dynasty took power, they began rebuilding the city. Mesopotamian rulers considered construction a sacred duty. The tablet may represent what we would now call an urban planning blueprint, the oldest one ever found. Now, blueprints are one thing. A building plan shows intent. It shows design capability. What it does not necessarily prove is advanced engineering knowledge. For that, you need mathematics. The clay tablet known as Plimpton 322 sits in the Rare Book and Manuscript Library at Columbia University in New York. It is small, roughly the size of a smartphone, and it is broken on the left side. The tablet contains a table of 15 rows of numbers written in the base 60 number system that the Sumerians invented. When Mansfield and Wildberger at the University of New South Wales analyzed those numbers, they found that each row describes a different right-angled triangle. The numbers are Pythagorean triples, sets of 3 whole numbers, where the square of one side plus the square of the second side equals the square of the third. The first row, for example, references the triple 119, 120, and 169. The 15 rows form a sequence of triangles with steadily decreasing inclination. This is effectively a trigonometric table, and according to Mansfield's research, it was not just functional. It was more accurate than the trigonometric methods that would later be developed by the Greeks, because it avoided the rounding errors inherent in working with irrational numbers. The base 60 system allowed the Sumerians to express ratios that our base 10 system cannot capture without approximation. Mansfield described Plimpton 322 as a tool that could have been used for surveying agricultural fields or calculating structural specifications for temples, palaces, and step pyramids. A working engineering calculator pressed into clay in the ancient city of Larsa nearly 4,000 years ago. And Plimpton 322 is not an isolated case. Another tablet, known as YBC 7289, held at Yale University, shows a square with its diagonal drawn in. Written along the diagonal is the calculation of the square root of 2, accurate to 6 decimal places. That level of mathematical precision was not matched in Europe for over 3,000 years. This was not abstract number play. The square root of 2 is the ratio between the side of a square and its diagonal. It is one of the most fundamental calculations in construction and engineering. If you are building anything with right angles, you need this number. The Sumerians had it pressed into a palm-sized clay tablet, ready for use on a job site. The mathematics was real. The blueprints were real. The question is whether the physical technology matched. And the answer, based on recent material science, is yes. In February 2026, a research team published a study in the Journal of Archaeological Science that should have gotten far more attention than it did. The researchers analyzed 59 samples of bitumen-based composite materials recovered from Abu Tabira, a major Sumerian urban center located near the famous city of Ur in southern Iraq. Bitumen is a naturally occurring petroleum substance, essentially a crude form of asphalt. In Mesopotamia, it was everywhere. The Sumerians used it to seal boats, waterproof storage containers, bind tools together, and construct buildings. What the researchers expected to find was evidence of trial and error usage, a primitive society slapping naturally occurring goo onto things and hoping it held. What they actually found was the opposite. Using high-resolution digital microscopy and machine learning algorithms, they identified 4 distinct categories of bitumen composite, each with a different engineered formula tailored to a specific function. Adhesives designed for mounting flint blades into sickle handles contained high concentrations of plant fiber for flexibility and crack resistance. Standardized trade ingots showed a homogeneous mix of both plant and mineral materials, suggesting they were semi-finished products prepared for transport and later adapted to specific uses at their destination. Waterproofing sealants had their own distinct composition. And a 4th category, mysterious spherical objects, whose function remains unknown, showed the most uniform internal structure of all. The researchers described these as technological recipes, not random mixtures. Recipes. Repeatable, consistent formulas that Sumerian craftspeople followed across multiple production batches. The study also found microscopic evidence of systematic recycling. Bitumen was too valuable to discard. Broken tools, dismantled boats, and production scraps were collected, reheated, and reprocessed. Repeated heating left detectable signatures in the material. Too many heating cycles made the composite brittle, and the Sumerians knew this, limiting how many times a batch could be recycled. Modern engineers who reviewed the findings pointed out something remarkable: the principles behind these Sumerian formulas, adding fiber to control flexibility, incorporating mineral fillers to increase rigidity, and managing thermal degradation through controlled recycling, are the same principles used in modern asphalt engineering today. The Sumerians arrived at these solutions without formal scientific theory, without chemistry, and without materials, science as a discipline. They got there through observation, experimentation, and 4,000 years of accumulated practical knowledge. This was not a civilization fumbling in the dark. This was industrial-scale material engineering, and they applied that engineering to water, which in southern Mesopotamia was both the greatest resource and the greatest threat. The land between the Tigris and the Euphrates rivers was flat, marshy, and prone to catastrophic flooding. Without intervention, the rivers would destroy crops one season and leave fields parched the next. The Sumerian response was one of the most ambitious hydraulic engineering projects the ancient world ever produced. They built canal networks stretching across hundreds of kilometers, lined with mud brick and sealed with bitumen to prevent leakage. They constructed levees along the riverbanks using baked mud bricks to prevent erosion during flood season. They engineered sluice gates to regulate water flow between canals and agricultural fields. During the dry season, they deployed shadafs, mechanical water lifting devices depicted on cylinder seals dating to approximately 2200 BCE, to raise water from low-lying river channels up to the level of their fields. The shadaf itself is a simple machine, a counterweighted lever that allows a single operator to move large volumes of water with minimal effort. It is elegant in its efficiency, and some scholars have proposed that a more advanced water-lifting device, the Archimedes screw, may have actually originated in Mesopotamia rather than in Greece. The Assyrian king Sennacherib, who ruled in the 7th century BCE, described casting a water-raising device in bronze for his palace gardens at Nineveh. The description matches the mechanics of a helical screw inside a cylinder, the same device traditionally attributed to Archimedes several centuries later. 18 separate canals have been documented bringing water to Nineveh alone. That is not a village irrigation ditch. That is a metropolitan water distribution system, engineered and maintained at the scale of a modern utility. The Sumerians also gave the world the true arch, an invention of the 4th millennium BCE. The arch solved a fundamental problem in construction. How do you create an opening in a wall that can still bear weight above it? The Sumerian solution transferred the load outward and then downward into the ground, rather than concentrating it directly above the opening. By building a series of arches back to back, engineers could construct vaulted tunnels and covered passages. This principle remained the backbone of structural engineering for 5,000 years, right up through the Gothic cathedrals of medieval Europe. All of this was accomplished by a civilization that had almost nothing to work with. The Sumerians had no forests for timber. They had almost no stone. They had no metal deposits. What they had was clay, river reeds, and bitumen. And they built a civilization out of those three materials that lasted for over 2,000 years. Philip Jones, an associate curator at the Penn Museum in Philadelphia, has described the Sumerians' true genius as organizational. They adapted technologies that had been invented elsewhere and applied them on a vast scale. They created standardized systems of measurement, writing, law, and administration that allowed complex engineering projects to be planned, coordinated, and executed across entire city-states. Their base 60 number system, the one that gave us the 60-second minute and the 360-degree circle, enabled calculations of a precision that would not be replicated for millennia. And 500,000 clay tablets have survived from the civilization. They were preserved not by design, but by accident, baked hard by the fires that destroyed the buildings they were stored in. Most of them sit in museum collections around the world, untranslated and unread. Only a fraction of what the Sumerians recorded has been studied. The mathematical world, as Daniel Mansfield put it, is only beginning to wake up to the fact that this ancient but highly sophisticated culture has much to teach us. There is a tendency in popular history to treat ancient civilizations as primitive, to assume that because they lacked our tools, they lacked our understanding. The Sumerians did not have electron microscopes or computer modeling. They could not run finite element analysis on their building designs. They had clay, a sharpened reed, and the accumulated wisdom of generations of engineers, surveyors, and craftspeople. And with those tools, they calculated the square root of 2 to 6 decimal places. They built trigonometric tables that surpassed Greek methods in accuracy. They engineered composite materials using principles that modern scientists validate with machine learning algorithms. They drew city blueprints so precise that it took aerial photography to confirm them. They designed temples whose structural innovations would not be matched for 1,000 years. The blueprints are real. They are sitting in museums in Paris, New York, Philadelphia, and Girsu. The mathematics is confirmed. The material science is published in peer-reviewed journals. The only thing missing is a satisfying explanation for how a people with almost no natural resources, living in a floodplain 5,000 years ago, figured all of this out before anyone else on the planet.